we've discovered something about polarity. What we're going to do is we're going to start to relate this to what we call intermolecular attractions. And these intermolecular attractions are basically broken down into three different categories. We have London forces, which are actually created between non-polar substances. So this is created by non-polar. We have dipole-dipole, which means two poles. So polar substances. And then we have hydrogen bonding, which is created between extremely polar substances. And so what we're going to do is we're going to work our way through each particular type of this. And so let's start out with the London force. Now, London forces are nonpolar molecules, and what is created is an instantaneous and an induced dipole. What you're seeing in these molecules to the side is we get these electrons that are actually flying around inside these objects. So we have a little electron here and an electron here. And what they do is they move into those positions. So that would be actually an instantaneous dipole. And they move over for a moment. And by doing that, they cause an induced dipole. So that one's induced, this was instantaneous. Well, they don't like to be in that particular situation, so what happens is the electron charge moves back the other direction, causing another instantaneous dipole, which also induces this particular molecule. And so it's not a very strong bonding. What we're doing is we have these electrons bouncing back and forth, and so the molecules themselves don't tend to be attracted to one another very, very well. And so in London forces we have weak intermolecular attractions, things like methane, pentane, butane. Butane is a gaseous form because it's not really, each molecule is not all that attracted to its neighbor. And so what it does is it goes into a gaseous form very easily. So moving on to a dipole. If we look at this particular molecule, what we have actually is a carbon in the middle. We have a hydrogen out here, hydrogen, hydrogen, and then we have this chlorine off the end. And the second molecule is exactly the same. What happens is the electron density is moving towards carbon between the hydrogens. And so if we drew arrows, they're all kind of heading that direction, which makes each one of these hydrogens slightly positive. Okay, so we have this end that is slightly positive. And between chlorine and carbon, you'll notice we have 2.5 and 3 for our electronegativities. So the electrons are tending to move out towards chlorine, and so it makes this end slightly positive. Now, that means if we have two poles, we have a greater attraction for the molecules of similar type or of types that would have some sort of charge. And so what we get is we get an attraction between that hydrogen and that chlorine, and so we get this attraction, and it's a magnetic attraction. So we have a positive end, this should be a negative end attracted to these positive ends over here. And if we have a whole bunch of these, they're going to be aligned so that the positives and the negatives attract one another. Any compounds that are polar are going to have an attraction similar to this. Moving to the next molecules, we actually have hydrogen bonding, and I haven't put that up here yet, but this is hydrogen bonding. And hydrogen bonding is created between two molecules that have a hydrogen-oxygen bond, a hydrogen-nitrogen bond, or a hydrogen-fluorine bond. And what occurs at the hydrogen-oxygen bond, you'll notice that this hydrogen here is attracted to this oxygen. And that bond, they're both very, very these two molecules are very, very polar. So the attraction between these magnetic forces is very, very high. And so you'll see that these two attract each other very well. And some of the properties we'll get to in a little later deal with this attraction between these two things. And so when we're dealing with molecules, if we have a long carbon chain and all of a sudden off the end of this carbon chain we have something like a nitrogen sticking off the end, what will happen is another hydrogen-nitrogen molecule will be attracted to it. And what you'll get is you'll get that, again, you'll get this hydrogen bonding between these two. And so it's very important in hydrogen bonding that you have hydrogen, oxygen, hydrogen, nitrogen, or hydrogen fluorine. And that's due to the extreme difference in electronegativity. Anything other than that doesn't have a strong enough or large enough difference in electronegativity to cause this hydrogen bonding. Water, for example, this is a particular molecule of water, or a series of waters, basically what we'd see in a solution. What we have is an attraction between a hydrogen and an oxygen all the way around, and so it tends to stick together because of those polar attractions. Another one, if we look at DNA or we look at RNA or we look at polymers, a lot of times they talk about hydrogen bonding. Well, that hydrogen bonding, if you notice again, are these little dotted lines in here. And those little dotted lines are between the hydrogen, oxygen, hydrogen, oxygen. And notice on the other end we have this nitrogen. That's really important to make sure that that attachment is there. And the same over here, we have this hydrogen, oxygen, but there's a nitrogen that's actually bonded to the hydrogen. Okay, and so we get this nice hydrogen bonding all the way across here. Okay, we will start to talk about, well, how does dipole, London forces, and hydrogen bonding affect the states of matter and how they're important to the states of matter in the next short video.